In many cases, the estimates we use are mean. And when we are dealing with more than one population, and we want to draw inferences about both the population and wanted to observe if there is any similarities or if there is any real difference between the two populations, we want to observe and calculate certain estimates. In this module, we will be talking about the estimates using the sampling distribution of difference between two means. Before we go further, we will talk about a quick review regarding the sampling distribution of mean. The first is when the sampling is carried out from a normally distributed population with a known population variance, then the mean of the sampling distribution of x bar, that is mu x bar, will be equals to the population mean. Whereas the standard error of x bar, which is also known as the standard deviation of the sampling distribution of mean, is equals to sigma divided by root of n, where sigma is the population standard deviation. And moreover, the sampling distribution of x bar is normal. And the second condition is when the sampling is from a non-normally distributed population with a known population variance. Then again, the mean for the sampling distribution of x bar will be equals to the population mean. Whereas the standard error of x bar will have two conditions. That if n ratio capital N is less than 5%, it will be equals to sigma over under root n. Otherwise, the standard error will be equals to sigma over under root n multiplied by this small correction factor, which is n minus n divided by n minus 1, the square root of the whole thing. Moreover, we assume that the sampling distribution of x bar is approximately normal in this situation. Hence, carrying out the same idea, in practice, we would not attempt to construct the desired sampling distribution for the differences in two sampling means. But we can conceptualize the whole idea in this manner, that when we are sampling from the finite population, we need to follow few steps while we construct the sampling distribution of the difference in means. First of all, we will select all possible samples. When all possible samples can be counted by n1, choose n1. Here, capital N1 is the population size and small n1 is the required sample size. Hence, first of all, we select all possible sample of size n1 from the population capital N1 and compute the mean for each sample. Similarly, for the population 2, we will obtain all the possible samples n2, choose n2 of size n2 and compute the mean for each sample. Once the means for each samples for all possible samples from the population 1 and the population 2 have been calculated, we take all possible pairs of sample means, one from population 1 and one from population 2, and hence we take the differences. Here is the working table for the construction of this distribution of the differences between two sample means. The first column represents samples from the population 1, whereas second column represents all the possible samples from population 2. Third column represents sample means that we obtain from all the populations of sample, all the possible samples of population 1 is given in the third column, and similarly in the fourth column we will have sample means for all the possible samples coming from population 2. And hence, since our desire is to construct the sampling distribution for the difference between two sample means, we will take all possible differences between the means coming from all possible samples of population 1 and population 2. And hence, we use this information to construct a sampling distribution. We will list all of these observations as mutually exclusive categories and we'll make a frequency distribution as well as a relative frequency distribution, upon which we will further estimate the mean of the sampling distribution of the difference in sample means, as well as the variance and standard error for the difference between two sample means. Just look at the pictorial representation. We have a population 1 with mean mu1, and there is another population, that's population 2, with mean mu2. Over here, we made it pretty symmetric, and we are assuming that both these populations are normal, but this shouldn't have been the case all the time. Hence, from this two population, we take two sampling distributions, and two sampling distributions are also pretty normal. So the first picture represents the sampling distribution of x bar 1 that comes from this all possible samples from the population 1, and second represents the sampling distribution of x bar 2, the all possible samples coming from population 2. Hence, since our interest is knowing the sampling distribution of the difference in means, hence the last distribution is also going to be normal. And the difference, the sampling distribution of the difference of x1 bar, which is the sample mean for the first population, minus x2 bar, which will be the sample mean for the second distribution, the second population, will be again going to be normal. Moreover, it will have certain mean. And if we are taking the difference of two population means, then the mean of the sampling distribution of the difference in mean will be represented by mu x1 minus x1 bar minus x bar 2, which is equals to mu1 minus mu2. Here, mu1 is the mean of the first population and mu2 is the mean for the second population. Similarly, sigma square x1 bar minus x2 bar represents the variance for the difference for the sampling distribution of difference in means, which is equals to sigma 1 square over n1, which is going to be the variance of the sampling distribution of x1 bar, and sigma 2 square over n2, which is the sampling variance for the sampling distribution of difference in x bar 2. And from here, we will notice that the overall variance for the sampling distribution of difference in means equals to the sampling variance of the population 1 and plus the sampling variance of the population 2. From here, we can give two notes. The first is that means of two distributions can be subtracted from one another, or they could be summed from one another using standard arithmetic operations. When we are interested in knowing the sampling distribution of x1 bar minus x2 bar, that's when we will subtract their means. But when we are interested in knowing the sampling distribution of x1 bar plus x2 bar, we will be adding up their individual population means. The second important note that we can observe from this methodology is that since the overall variance of the sampling distribution will be affected by both contributing distribution, the variances will be summed up. Even if we are interested in the difference of the means, this also assumes that two distributions are independent. And here we will be using a usual property of the variance, where variance of x1 bar plus x2 bar and variance of x1 bar minus x2 bar both will be equals to the variance of x1 bar plus variance of x2 bar. And since we are assuming they're both are independent, so the covariance for both the variable will be equals to 0. Hence, we know that the normal distribution described above can be transformed to the standard normal distribution, where in standard normal distribution, if we are interested in x, then we will subtract its mean and divide it by its standard error. Here, our interest is transforming x1 bar minus x2 bar into the standard normal, when we already know that x1 bar minus x2 bar has the normal probability distribution. Then to transform it into a new variable, new standardized variable, that is z, which is standard normal distribution, equals to a random variable, which is x1 bar minus x2 bar, minus mean of the random variable, which is mu x1 bar minus x2 bar, hence it is equals to mu1 minus mu2, divided by the standard error, where standard error is the standard deviation of the sampling distribution of difference between two means. Hence, it is root of sigma 1 square over n1 plus sigma 2 square over n2, where sigma 1 square over n1 represents the sampling variance of the population 1, and this represents the sampling variance for the population 2. The theoretical results here is that the whole idea is based upon that can be summed into the following statement: that given two normally distributed populations with means mu1 and mu2 and variance is sigma 1 and sigma 2 square respectively, the sampling distribution of the difference x1 bar minus x2 bar between the means of independent samples of sizes n1 and n2 drawn from these populations is normally distributed with mean mu1 minus mu2 and variance under root of sigma 1 square over n1 plus sigma 2 square over n2. This procedure we just followed is valid even when the sample sizes are different and the population variance have different values. Many times a researcher is faced with one or other of the following situations. One is sampling from non-normally distributed population, and the other is sampling from population whose functional forms are not known. But there is a solution to this problem, that to take the large sample. Since when the sample sizes are large, the central limit theorem applies, and the distribution of the difference between two sample means is at least approximately distributed as normal distribution, and hence it makes it easier to convert any random variable using these asymptotic property into the standardized normal random variable, and it helps us to calculate the probabilities using all these estimates. Hence, the sampling from non-normal populations with a large sample size, it will still be the normal with mean mu x1 bar minus x2 bar with standard deviation sigma x1 bar minus x2 bar. One should know that the estimates obtained using the sampling distribution of the difference in the means help significantly to draw inferences about the two populations if they are on average equal or not. Thank you.